Welcome back to all our participants. Thank you very much for being in this second part of the school of today. We will start then with Professor Cristina Garcia Vergara with the exercises. Remember that the PDF file was sent to your email, each one of you. So if you have any problem trying to download the information, or if you didn't receive it, you can either post something in the chat and we will try to send you again the information, or you can go to Christina's webpage. Christina will send us through the chat the webpage because I forgot to write it down. Sorry, Christina. So in that sense, you can go to the webpage and she will be able to, you will be able, to download the PDF file as well. So thank you very much, Christina, and the space is yours, and I will just post the address in the chat.
Great, thank you. And I also just upload the lecture too. Then you can also check in the webpage what we talked in the past 2 hours. And I'm gonna start sharing. Okay, then as I told you before, in the workshop today, we are gonna, open this. We're gonna to compute the clustering of a galaxy catalog. Then let me first remember what we did yesterday, in case you were not participating here. Yesterday, we work, where is that? This one. Yeah, yesterday we worked with a simulation, the site simulation. Then we download the catalog from the web page. This is a catalog of the position of galaxies or dark matter halos in the universe in a square region. This catalog contains redshift information as well as coordinates and some other physical parameters of the galaxies. Then, then what we did was to, maybe I can show this here. Yeah, what we did was basically to download the catalog. And we focused on a sample of galaxies at redshift between 1 and 1.5. And for galaxies in that redshift range, we created 2 different samples of galaxies. One that we call the low mass galaxies with halo masses between 1 times 10 to the 11 and 1.12 10 times to the 11. And one sample with more massive galaxies in this in this mass range. Then we created these 2 catalogs, and we were computing the number of sources in the catalog, which is like around 10,000 for each one. We compute the median of the halo and make some plots. Then I'm gonna show you the plots here. In case you didn't got the plots by yourself, you can download the plots in my webpage in workshop 1. I put all the outputs from the practical part of the workshop 1. Then this is the redshift distribution for both samples. Then the main message here is that both samples are similarly distributed over redshift space. This is the distribution of the halo mass for each galaxy. Let me recall that here we call them halo. Every galaxy is called halo here because galaxies are dark matter halos actually. And as I explained yesterday, when you make a simulation, you normally simulate the parent halo, which is the big halo that I explained you to form from collapse in the lecture 1. And this parent halo normally contain several galaxies, which are called subhalos. But then in this catalog, we have the halo mass for each individual galaxies. Then that is why we call this halo mass here. And one of the sample, the less massive sample, has a very narrow range in halo, because we built the samples such that we have similar number of sources in both of them, and given that in the universe in general we have more sources with lower masses, then to get the same number of sources for the more massive galaxies, we have to cover a wider range in halo mass here. But the important part is that the median halo for the two samples are very different. We also plot the sky distribution for both samples. Then this is just the ray ascension and declination for both of them. This is for the low mass catalog, and this is for the high mass catalog. I ask you to check just by eye if you can find any difference between them in terms of clustering. And basically the message here is that at least I cannot detect any difference by eye only. I couldn't say which population is more clustered than the other. And then that is the importance of have a mathematical description of this. And we will check after to measure the clustering of these two samples. We will check if really the clustering is similar as we see by eye from these two plots or not. And yeah, I think that was all what we did yesterday. Okay. Then today, this is workshop 2. We will use those two catalogs to measure the angular clustering of the galaxies for both samples. In this case, I know we have redshift information too, but I would like that we measure only the angular clustering. Then we will forget about redshift information just because it's more simpler. Then I think it's more reasonable to finish in a 1-week course. However, as you saw, we just selected galaxies in a relatively small redshift range, only galaxies between redshift 1 and redshift 1.5, sorry. Then the dilution of the signal shouldn't be so important in this case. Then we will measure the angular clustering. We will start today, and we will finish with this tomorrow, because this includes several steps. Then if you were not successful creating the files with the sample of the galaxies yesterday and the plots, you can download those from this page that I put here. That is my web page in workshop 1. Here in results, you can find the high.dat and low.dat, which are the galaxy samples for the low massive and high massive galaxies. Output is just the output that I got in the console when I asked you to output the number of galaxies of the sample and the median mass. Then you can check the numbers there. And plots are the plots that I just showed you. And you can download those catalogs here if you couldn't create your own. Okay, then today I'm gonna follow a little bit different structure than yesterday, because yesterday I was reading the statements here and giving you some time to work by yourself, but today I'm gonna do this in the other way around. I will read this statement and I will show you how can I do that. Again, I'm ideal programming, not Python. Then you can follow the algorithm, but don't try to follow the syntaxes, even when the syntaxes, I guess, is pretty similar. But then you are gonna understand what I'm doing. But but I'm going to show you what is the algorithm to do that. And after that, I'm going to give you some time for you to create your own code in Jupyter Notebook or anything that you prefer. I also would like to invite you to send me your codes and send me your plots to check what you are doing. And if you have questions, of course, you can ask me at any time or by email also. Okay, so let's start. Then first, make sure that you have the files load at that and hide at that in your working directory. Then those are the files that I just showed you. I will gonna be working in my directory. Then I have those two files here. Yeah. Then the first step we need to make is the creation of the random catalog. Then we will start with that. Then for that, first we need to open the sky distribution plot that we created yesterday and check the minimum and maximum values of the ray ascension and declination for the galaxies in the samples. Then we are going to choose one of the samples. Then for now, I can choose the low mass sample. It doesn't really matter which one we start with. The random catalog will be the same for both of them because the geometry of this simulation is the same, of course, for both samples. Then yeah, I'm going to start reading the catalogs here. Read call. Yeah, I hope you can see this well. Then this is high, that, area, high, tech, high. I'm just reading the catalog that we created yesterday. Low, declination, low. Oops. Okay, and if you open the plots from yesterday, those plots, you can see that the both coordinated ray ascension and declination goes from 0 up to 1.4 degrees. Then we have to create a random catalog covering exactly the same area. In this case, this is easy because this is a simulation, then you just have a square region in the sky. But in reality, when we observe the sky, the survey coverage doesn't really very so nice like this one. You have like starting that you don't have a square region in the sky. You can have like different shapes, and you also have some holes in between. Then it's a little bit more complicated, but for now we are just using this one. Then that is nice. Maybe in other workshop I can show you how is this when you work with observations. But well, we have to create a random catalog covering the same ray ascension and declination as this one. Then we will start with that. Then we just define. This is creating the random catalog. We just define a mean 0 degrees and maximum and minimum declination. You can also start coding together with me in Python. But I will give you anyway some time after me for you to code this. This is thick. Oops. I cannot talk well while I'm coding. Okay. That is correct. Okay, then to generate the random points, we have to generate random declination and random ray ascension. Then in this case, I don't want to use so much time doing this. Then I will just copy here this. In this case, well, the syntax in IDL is this, but basically I just generating randomly distributed sources, 10,000 randomly distributed sources between the minimum and maximum right ascension. And I repeat the same for the declination. And in Python, I think you can use something like this command, that is numpy.random.uniform. That should be the right command to use in Python. Probably you have to import the numpy library, but that should be more simpler than this one. I think that you just have to provide the minimum and maximum value and the number of sources to create. Okay, then we are done with our random catalog. And then we have here. Yeah, generate the 10,000 random values. That is what we already did. Remember to use an uniform distribution. That is important because we need 0 clustering signal in this catalog. And yeah, I'm saying here that we normally should create a much larger random catalog because our data catalog contains already like 10,000 sources. Then normally we should create a random catalog with 10 times that amount or 20 times that amount. But we are just creating 10,000 to decrease computational time. Then afterwards, you can increase this number, but this will take a little bit longer to run. Then that is the reason why I choose 10,000. But of course, we should use a larger number. Our results are not gonna change so much anyway. Then save a file with the positions of the random catalog, and also make a plot of the sky distribution of the random catalog. And I'm gonna do that now. Open write. I will call this random that then this is just to write the file. Okay, this part will write the file. Then I'm gonna run this so far to check that everything is running correctly. Yes, it is working. And now I'm gonna plot the random catalog that I just created. Then again, I already did that to save time. This is just some definitions in ideal to create a plot that looks a little bit better. Then here I just gonna plot the position of the random points. I can choose a size for the plot, and I don't know, this is just to make it better. Okay, title random catalog. Then what you should get here, if I run this, I can open plot random, this one here. And this is my random catalog. Then by eye, you can see that is very random. I ask you to compare this one with the one of the data, the sky distribution of the data. Then I will leave this to you. Compare the catalog, how they looks like, and we can comment this after you create your random catalog. Then now I'm gonna give you some minutes, maybe 10 minutes, for you to work on this 4 first points. As you see, this are not like complicated at all. Then I guess 10 minutes is fine for you. Then I'm gonna stop sharing here, and I'm gonna be here for questions or at any time. And I'm gonna be back in 10 minutes. Hopefully you will have created your random catalogs and your plots, and you can think about the question that I make. Okay, I'm back. I hope all of you or most of you could finish the random catalog. If not, it is okay. You can work on that later. And I encourage you to send me your code and your plots. Then I can check how are you doing with this. I will share my screen again. Then, as I mentioned in the last part, this is the random catalog that I created. You can see that the coverage in both right ascension and declination is the same as for the data. And I can probably put this on the side. This is the catalog of the data for the low mass case. Well, the points are a little bit different, but you can see, well, maybe it's not very clear by eyes, but this has not any pattern at all. This is the random catalog, and from the catalog, you can see much more pattern. And you can see that galaxies tend to be more clustered. For example, here we have much more accumulation of galaxies, and we can find several places in which galaxies are very close together. This is another example. Then if we see this in detail, by eye, we can actually check, for example, look at this accumulation of galaxies. We have a lot of galaxies in this small region. This kind of patterns are not happening here that often. Of course, we have in some cases, like for example, here we have some little accumulation of galaxies, but in general is much less strong than in the catalog. Then that is just to show you that our random catalog doesn't contain any clustering signal. Okay, so we can continue with the point number 5 in our workshop. The next step is to define the logarithmically spaced bins for measuring the clustering. Then for that, we have to define a minimum and a maximum value for which we are gonna to measure the clustering, and also a number of bins. These 3 parameters are very arbitrary. It depends on your interests. If you are interested to measure the clustering at very small scales, you can use a minimum value of 2 arcseconds, for example, like to trace the very close separation between galaxies, and a maximum value of, I don't know, 100 arcsecond. But if you are more interested in measuring this over a larger scale, you can go until 1000 arcsecond if you want. But the thing is that at large scale, you expect to have a much weaker clustering, then your signal will not be that strong. But you can play a little bit with those minimum and maximum values. For this exercise, I just choose to measure from 5 arcsecond until 200 arcsecond, but you can play a little bit with that. And you also can always choose a different number of bins. Then here I'm suggesting to use 7 bins, but if you choose more or less bins, that is also fine. Then we have to create logarithmically spaced values. I'm here providing you what is the function that you can use for that in Python. It's a really easy way to create this in Python. Actually, with this command, you have to just provide the minimum and the maximum and the number of bins, basically. Store those values in an array that we will call array theta begin. And yeah, print the values of theta begin. Then I'm gonna do that part of the workshop now. Then I will, clustering parameters. Then we have to define a theta min, a theta max, and bins. I set this to be 5, this 200, and 7. That are just the number that I just told you. This 7, this is the number of points that I have. I want in my plot. Then, if I want 7 points, I actually have to define. I'm gonna define n beans, which is beans plus 1, because if I will define the starting point of each bean, then I have to define 8 starting point if I want to have 7 points in my plot. That is the only reason that I'm doing this. Then again, in this part, I will copy what I already did. Right, repeating this. This line here is just doing what you can do with log space in Python. Then in IDL, for some reason, is a little bit more complicated, but it's just a formula, an equation that gives you logarithmically spaced beans. Then instead of this one, you can just use numpy log space. I think you have to provide this limits. You have to provide 10 to the 5 and 10 to the 200. I think you can double check in Python, and the number of beans. Then for you, I guess is easier. And then this is the logarithmic of theta. Then my theta begin array will be 10 to the logarithmic of theta. Okay. And then I can just print theta begin. And this theta begin is the starting point of the bean, right? Then I'm gonna run this code. And this is theta begin. I'm gonna copy this here, that maybe is more clear for you. But basically this is, 5 if the initial point of the first bean by definition. And then this is the starting point of the second bean, and therefore is also the end point of the first bean. Then our first bean is defined by those 2 values. Then I'm gonna have one number of pairs between 5 and 8.5 arcseconds. Then that is what I mentioned before. If you have 8 theta begin values, then you will have only 7 measurements for the number of pairs, because those are your lower and upper limits. And then the last value here is 200 arcsecond. Then that is the upper limit of my last beam. Okay, I want to comment this. And then compute the beam width and print their values. I can quickly do this by just defining the beam width. It's gonna be theta begin. This is just the syntaxes in IDL. You can find your own syntaxes in your language, but that is, I'm just computing the difference between the theta begin and the theta begin, but shifted for one position. Then that is the beam width. The first position, of course, is gonna have not sense, because you are computing the difference between this one and the last value of the theta begin. Then that is not informative. Then I'm gonna actually create this is gonna be being width 1, and this is being width will be this same array, but between position 1 and the last one. Then I can print the values here, being width, to check that it does make sense. Yes. Then if I run this, here is the beam width. I'm gonna copy this here. Yeah, then it does make sense. The first beam width is 3.5. It's perfect. Okay, this is the output only. And in number 7, I ask you to make a plot of theta begin versus the beam width. Then we can check that you're doing the things right. And again, I have this already done here. This is just to open the file to make a plot, and I will just plot what I am asking, theta begin versus beam width. Then I can plot theta begin and beam width. Can define the axis. Yeah, that is all. Theta begin is, let me check. Okay, now I think that should work. Okay, then I can check the plot now. This one. And here's my plot. This is theta begin versus beam width. Then this is increasing the starting point of theta begin, and the beam width is also being larger and larger by definition because we are using logarithmically spaced beams. Then actually, if I plot this in logarithmic scale, I can obtain, oops, I can obtain, yeah, like equally spaced points in this axis. But the beam width is still increasing exponentially here. Then, yeah, I think you can work on this. We have 5 more minutes before the break. Then I will lead you to work in these points to create your beams, and I will return here in 5 more minutes. I think 5 minutes you can do it. Okay, it's almost time for the break. I guess maybe 5 minutes is too short for you to finish this part. Then we will take the break now for 15 minutes. And when we are back, I will give you 5 more minutes to finish until the part that we are so far, which is number 7 for this workshop. And then I'm gonna explain you how we will compute the DD array. I already included an explanation in the workshop sheet. Then maybe you can take a look at of it. But I'm gonna explain you also when we start this after the break. Then see you all in 15 more minutes.
Thank you, Christina, very much for this first part. I don't see any questions in the chat, so I think we can go to the break. We will convene back in 15 minutes, so 11:30 your time, 5:30 your time, and this will give also extra time for the people to finish the exercise they are doing. Maybe if needed, we can just give another 5 minutes if you consider this important in the next part. And if not, they can try to finish by themselves in these 15 minutes, and then we will continue from the point that you leave.
Sure, sounds good.
Okay, perfect. Thank you very much. See you all in 15 minutes.